What's up? I'm Vin, and today I want to show how to use the ratio test. So what we do for all these questions is we take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And three things could happen. The limit is going to work out to something less than 1, and in that case your series absolutely converges. If your limit works out to something greater than 1, then your series diverges. And in the case where the limit works out to be exactly 1, that means the ratio test is inconclusive, which means we have to use a different test. Now, the skills that you need to be able to do these questions, this is very algebra heavy, but you have to be really good at composition of functions. So you have to be able to replace x with x plus 1 or n with n plus 1. And you have to be able to do that with polynomial functions, exponential functions, or functions that have factorials in them. So this is just some of the algebra that you need to be successful with these questions. For the questions we're looking at, we're going to use the ratio test to determine if the series converges or diverges. So to use the ratio test, what we're doing is we're taking the limit as n goes to infinity, and we're taking the a sub n plus 1 term. So that means we're going to replace every one of these n's with n plus 1. So we're going to have 10 to the n plus 1 instead of n over, and then instead of n plus 1 in parentheses, I'm going to put the plus 1 at the end, but we're replacing that n with n plus 1. And then we have times 4 to the 2n plus 1 is going to change to 2 times n plus 1 in parentheses plus 1. So you have to be careful for pieces like this. Don't just write 2n plus 1 plus 1. We have to make sure to put parentheses and distribute. So now what we're doing is we're dividing a sub n plus 1 by the original. And notice the original term in our series here is a fraction. So when we divide by a fraction, we could use keep, change, flip, or we're just going to be multiplying by the reciprocal of this original fraction. So we're going to have n plus 1 times 4 to the 2n plus 1. And then this is, let's just make that a little neater, over 10 to the n. So the step that I skip, so this is really what we're doing on the side here, is we're doing 10 to the n plus 1 over, and then we'd have n plus 1 times 4 to the 2n plus 1 plus 1. Technically, we're doing this here, divided by 10 to the n over n plus 1 times 4 to the 2n plus 1. But once again, I personally skip this step every time, and I will skip it after question 1, because to write this limit expression over and over just to show the division of two fractions just takes up a lot of time. So this step here, after you go through a few of these, you tend to just skip this step and jump right into it. So now let's go ahead and simplify this. So what we have here, this is now the limit as n goes to infinity. And one thing we could simplify right away, 10 to the n plus 1 over 10 to the n simplifies to 10 to the first. So this is going to cancel this out, and we're left with 10 to the first. And the way I do that quickly is I just see n plus 1 is 1 more than n. So that's why we're left with a 10 to the first on top. And now what we could do is write the leftovers. So we have 10. And then the rest of what we have on top here is, well, we're going to have times n plus 1 times 4 to the 2n plus 1 over, and then n plus 1 is n plus 2. And then we're going to have 4 to the, and if we distribute this, this is 2n plus 2. So this here simplifies to 2n plus 2, but then plus an extra 1 will give us 2n plus 3. So now we could simplify a little bit more. This is going to be the limit as n goes to infinity. And notice here we have 4 to the 2n plus 1 over 4 to the 2n plus 3. So right now in the absolute value we have 10, we have n plus 1. But when these cancel out, notice the denominator has the higher power. So we have 4 to the 2n plus 3 versus 4 to the 2n plus 1. But 2n plus 3 is 2 more than 2n plus 1. So that means on bottom we're going to be left, when these cancel out, we're going to be left with the 4 squared on bottom. Here like this. We could go on a side quest here and show that if we did this division 4 to the 2n plus 1 over 4 to the 2n plus 3, that technically this is 4 to the 2n plus 1 minus 2n plus 3. And this would become 4 to the 2n minus 2n cancels, and then 1 minus 3 is negative 2, and 4 to the negative 2 is the same thing as 1 over 4 squared. So we could show all that here, but once again, depending on how strong your algebra is, like you could just skip over steps like that. So yeah, anytime you're using the ratio test, it's just a ton of algebra that you have to go through. So we have this here. And now notice, since n is going to infinity, we could get rid of the absolute value because we have all positive stuff here. And what I'm going to do is this constant I'm going to factor out of the limit. So now this is going to be 10 over 16 when we do 4 squared times the limit as n goes to infinity of, we have m plus 1 over m plus 2. And once again, because n is going to infinity, m plus 1 over m plus 2 is positive. So we could get rid of the absolute value. And now we'll just simplify this. 10 over 16 simplifies to 5/8 times, and this limit is going to go to 1 because the leading terms match. They have the matching powers and matching coefficients. So this is 5/8 times 1, which is equal to 5/8, which is less than 1. And notice this falls under our first case, that by the ratio test, we could say that our original series converges because our limit worked out to something less than 1. Now, one thing worth mentioning here is that we had to determine if the series converges or diverges. But if our series absolutely converges, that means that it also just converges in general. So for this next question here, we're going to be using the ratio test again. And we're taking the limit as n goes to infinity. And we're starting with the a sub n plus 1 terms. We have negative 1 to the n plus 1. Then we have 1.1, and we're replacing this n with n plus 1. Over, instead of n to the 4th, we have n plus 1 to the 4th. So I'm going to pretend here that I don't know we could use the nth term test for divergence, but we're going to see that the ratio test can be used here to show that this series diverges. So now, once again, we're going to be doing a sub n plus 1 divided by a sub n. So just think of this term here. This is our a sub n term, and what we have starting here is a sub n plus 1. So when we divide a sub n plus 1 by a sub n, we're just going to be multiplying by the reciprocal. So we have n to the 4th over, and we have negative 1 to the n times 1.1 to the n power, and we just throw in our absolute value here. So now what we're going to do is we're just going to simplify this a bit. This is equal to the limit as n goes to infinity, and what we have here is 1.1 to the n plus 1 over this. 1.1 to the n cancels out completely, and we're going to be left with an exponent of 1 here because n plus 1 is 1 more than n. And now negative 1 to the n is gone, and we're going to be left with negative 1 to the first on top because, once again, n plus 1 is 1 more than n, so we could cancel those out. So now what we have is we have negative 1, we have times 1.1 to the first, and then what we have left after it is n to the 4th over n plus 1 to the 4th. And we have our absolute value. Now the absolute value is going to get rid of that negative 1, and the 1.1 we could just factor out. So this is 1.1, just make this neater, times the limit as n goes to infinity. And now we could get rid of the absolute value on this stuff because n to the 4th is positive and n plus 1 to the 4th is positive as n goes to infinity. So we have n to the 4th over n plus 1 to the 4th like this. So at this stage, we could evaluate this limit. And let's just give ourselves space. So we're going to extend the page here. So this is enough for us to answer this limit because when you're doing limits at infinity, and you have a rational function here on the inside of your limit, the only terms that matter for determining limits at infinity are the leading terms. So what I imagine for this question here is, what happens if I were to expand n plus 1 to the 4th? Well, we would have a really messy expression, but the leading term would be n to the 4th plus some number times n to the 3rd and so on. But the only term that we need for limits at infinity are the leading terms. So I could just say that this is the limit as n goes to infinity of n to the 4th over n to the 4th because that's the leading term of n plus 1 to the 4th. And this is just going to work out to 1.1 times 1. So this is going to be 1.1, which is greater than 1. So in this case, this is the second case of the ratio test. This would tell us by the ratio test that our original series diverges. For this next example, we're going to use the ratio test again, and we're taking the limit as n goes to infinity, and we have the absolute value of n plus 1 to the n plus 1 power. So we're finding a sub n plus 1 by replacing all of these n's with n plus 1. And on bottom, we have to put this part in parentheses. Instead of n factorial, we have n plus 1 factorial. So remember, this is a sub n plus 1, and our original thing is a sub n. So we're doing a sub n plus 1 divided by a sub n. So we're going to multiply by n factorial over n to the n. So remember, when we divide by a sub n, we're just multiplying by its reciprocal. And now this we just have to simplify. So what we're going to do to simplify this is that we have to break off some factors here. So this is the same thing as, we could say, n plus 1 times n plus 1 to the n power. So we're just taking away one of the n plus 1s so that we could create matching exponents with what we have on bottom. And now we have times n factorial over, and for this part here, we just have to be comfortable with expanding factorials. So n plus 1 factorial is the same thing as, we would have n plus 1 times n minus 1 times n minus 2, and this would go on and on and on to 3 times 2 times 1. So that's just by definition of factorial, but we're not going to go that far. We're going to stop at n plus 1, and then we're going to write n factorial after it, because n factorial would give you the remaining factors. And now we have times n to the n power. But why did we stop here? Well, we stop here so that n factorial and n factorial could cancel out. And that allows us to simplify this limit a little bit more. Notice before we write the next line, n plus 1 over n plus 1 also cancels out. So now this gives us the limit as n goes to infinity of, and notice we have n plus 1 to the n over n to the n, and both of those are, n is going to infinity, so these are two positive terms, so we could get rid of the absolute value. So now we have n plus 1 to the n over n to the n. So this is a little bit of an annoying limit to deal with, but one of the ideas we're going to use, so this is from way back in the day from algebra, when you have an expression like this, a to the c over b to the c, so you have two terms that have the same exponent, you could combine them into a single expression like this. So we could write this as a over b to the c. So that's what I want to do here. This is the limit as n goes to infinity of, and we're going to have n plus 1 over n to the n power. And if we simplify this a little bit more, this is the limit as n goes to infinity of 1 plus 1 over n to the n power like this. Now from here, the one challenge is that if you recognize this limit, this is the definition of e. So the limit as n goes to infinity of 1 plus 1 over n to the n is the limit definition of e. And Euler's number e is 2.718, and it goes on and on forever, but whatever that is, it's definitely greater than 1. And because e is greater than 1, our limit here, this tells us by the ratio test that our original series diverges. If you didn't know the limit definition for e, you would have to go through this limit using natural log, and that's a very messy process, so it definitely helps to know that definition of e. So let's go ahead and use the ratio test again. We have the limit as n goes to infinity, and now we're going to define our a sub n plus 1 terms. We have negative 1 to the n plus 1 is here, so we're going to have n plus 1 plus 1. We're replacing that n with n plus 1. Now these could be a little bit annoying to replace. So what we have is, instead of n factorial squared, I'll put a bracket here to give us extra space. We're going to have n plus 1 factorial, and this entire thing is being squared. So we're replacing the n with n plus 1. So that's going to be our term here. And then on bottom, we're going to have 2 times, and let me just write this a little bit better. So we have 2 times, replace the n with n plus 1, and then we have our factorial here. And then once again, this whole thing that we just wrote is a sub n plus 1. And this is a sub n. So just have to be very careful setting these up. This one, the algebra is definitely a bit tricky, that you want to make sure that you're replacing each n with n plus 1. So there was 3 of them to replace. And now we're going to be dividing by a sub n, which is the same thing as multiplying by the reciprocal. So we're going to have times 2n factorial on top over negative 1 to the n plus 1 times n factorial squared on bottom. So now let's make that a little bit neater. So we have n factorial squared, and there's our absolute value. So from this step, what we're going to do is we're just going to cancel out as much as we can before we write the next line. So let's see, we have the limit as n goes to infinity of negative 1 to the, and notice what we have here, negative 1 to the n plus 1 is negative 1 to the n plus 2. So just think of this, I'll just write it here as n plus 2. So when we do negative 1 to the n plus 2 over negative 1 to the n plus 1, this cancels out completely, and it leaves us with a -1 to the first on top. So we have absolute value of -1 to the first, and then here this is giving us n+1 factorial squared. So we're just going to write that out. We have n+1 factorial, and this whole thing is being squared. And then we have times 2n factorial, and then we have this one we're going to distribute. We have 2n plus 2 factorial like this, and let me make it so they both look like brackets. So 2n plus 2, although I could have used parentheses here, but whatever. Parentheses and brackets are interchangeable. And then we have n factorial squared. So now to simplify this, we just have to expand stuff a little bit. So what I'm looking at here is I expanded in such a way that the things that I want to cancel out will cancel out. So what I mean by that is, well, for one, absolute value of -1 is just going to cancel. So that's just going to become 1. So we could just get rid of this here because the absolute value is going to cancel this out. And now we could get rid of the absolute value. So n+1 factorial squared, I'm going to write as n+1 factorial twice. So just think of it like n+1 factorial. So n+1 factorial squared, we're just going to write out twice. This is n+1 factorial times n+1 factorial. But then I could expand this even more. This is the same thing as n+1 times n factorial, and the same thing with the other one, n+1 times n factorial. Now, why would I want to do that to the n+1 factorial squared? Why do we want to break it down like this? Well, you'll see what will happen. We have n+1 times n factorial, and then times n+1 times n factorial. And then on top, we still have 2n factorial. So this is just going to stay put for now. So on bottom, you see the n factorial squared. I'm just going to write this out as n factorial times n factorial. And I'm going to write it over to the right here because we need space to expand this piece. So n factorial times n factorial. That's how we're expanding n factorial squared. And the reason we write it like this and break this one down is so that n factorial cancels out this one, and this one here cancels out this one. So now, the next thing I want to do is I want to expand 2n plus 2 factorial, and we have 2n plus 2, and then 1 less than 2n plus 2 is 2n plus 1, and 1 less than 2n plus 1 is 2n, and I could throw in my factorial now, and now 2n factorial will cancel out 2n factorial. So you see, this simplifies a whole lot. So now this is equal to the limit as n goes to infinity of, and we'll make space. What do we have left on top? We have n plus 1 times n plus 1, and on bottom we have 2n plus 2 times 2n plus 1. And remember what we said before, we have a rational function here. So when you're taking the limit as n goes to infinity and you have a rational function, the only terms that determine the limit are the leading terms. So on top, the leading term would be the result of doing n times n, which is n squared, and on bottom, 2n times 2n would give you 4n squared. So this is going to cancel out like this, and our limit is equal to 1/4. And notice 1/4 is strictly less than 1. So by the ratio test, we could say our original series converges. And remember, if a series absolutely converges, that implies that the original series converges. For question 5, we're using the ratio test again. So we have the limit as n goes to infinity of, and we got absolute value, and a sub n plus 1 would be square root n plus 1 over 1 plus n plus 1 squared. So this is our a sub n plus 1. Our original a sub n is here, so when we divide by a sub n, once again, we're just multiplying by the reciprocal. That's going to give us 1 plus n squared like this, and then we have square root n on bottom. Now, one thing we could do right away is get rid of the absolute value, because all this stuff is going to work out positive since n is going to infinity. But the next thing I want to make use of here is from Algebra 1, or just way back in early algebra, when you have square root of a over square root b, that's the same thing as square root of a over b. So I want to use this idea to simplify. So once again, the absolute value could disappear, but square root n plus 1 over square root n, we could make into a single radical as square root of n plus 1 over n. And now we're going to, let's make that a little neater. So we have n plus 1 over n, and now we're multiplying by the leftovers. We have 1 plus n squared over, and then this would be 1 plus, we would have n squared plus 2n plus 1 if we distribute and expand this here. So now we just go through this piece by piece. But notice here, this limit, if we look at the leading terms, we have n over n, and this is going to work out to square root of, and the limit of the inside as n goes to infinity is 1, because n over n are matching terms. So the leading powers match and the leading coefficients. So we have square root of 1 times, and notice here the leading terms are n squared, and since they match every way, their exponents and their coefficients match, that piece is going to go to 1. So we have square root of 1 times 1, which is equal to 1. And this tells us that the ratio test here is inconclusive. Okay, so we have to be careful. Anytime you apply the ratio test and it works out to equal 1, that means the ratio test is inconclusive. That does not mean that the series diverges. That means we have to use a different test. Now, I covered the limit comparison test in a different video, but this previous question that we just did, we could show that this series converges by using the limit comparison test, and we would be comparing it to the following series here, to the series 1 over n to the 1.5. But I covered this in greater detail in a separate video. Now, for the last question here, we have the terms of a series are defined recursively by these equations, and we want to determine if the series from n equals 1 to infinity of a sub n converges or diverges. So what we want to do here is we're just going to do a little bit of algebra, and you see how we have these recursive equations. So we want to come up with an equation for a sub n plus 1 over a sub n. So what we could do is, if we have a sub n plus 1 equals 5n plus 1 over 4n plus 3 times a sub n, we could divide both sides by a sub n. And what that tells us here is it gives us a sub n plus 1 over a sub n is equal to 5n plus 1 over 4n plus 3. Well, then how does this help us? Well, note that when we use the ratio test, we're taking the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, which would give us the limit as n goes to infinity of, and we would have the absolute value of 5n plus 1 over 4n plus 3. Now, because n's going to infinity, that allows us to get rid of the absolute value. So if we really wanted to show every gritty step here, this would be equal to the limit as n goes to infinity of 5n plus 1 over 4n plus 3. But note, when we find this limit, we have n to the first versus n to the first. So the limit as n goes to infinity is just the ratio of their coefficients, which would be 5/4. And one comment we can make about 5/4 is this is a fraction that's greater than 1. So now we could write our conclusion here. Because the limit as n goes to infinity of this expression here equals 5/4, by the ratio test, we could say that the series a sub n diverges. Okay, well, this is going to conclude this video on using the ratio test. If this video was helpful, please like and subscribe. It really helps me grow the channel. And if you got any requests, just leave the topics you want me to cover in the comment section below. And thanks for watching.